Robotics and autonomous systems is really at a very crucial juncture, going from relatively low-dimensional systems to full-bodied humanoids. When you start from something like a mobile robot with only two directions of movement to something which is slightly more complex like a mini humanoid, to a Baxter or a PR2, robots which are bimanual with two hands and a head with some sensors, but it still cannot move. Then you have the additional complexity of robots like PR2, which have mobility along with dexterous manipulation of the hands. The problems, the scientific problems that are involved in solving and addressing some of the real-world challenges with these platforms increase in complexity.
We've already used robots to assemble the International Space Station, which was a collective of both humans and robots working together to build, the biggest thing ever built in space. We really see the next wave in human exploration starting with robots that will assemble a facility, and then people will arrive. So the robots will be taking care of it, kind of as what we call robot caretakers.
From NASA's perspective, building a humanoid is very crucial for unmanned missions to Mars. The kind of capabilities that are required of the humanoid includes dexterous manipulation, walking very robustly, opening doors, handling tools. So these are the kind of things that you and me take for granted, but it is very hard to incorporate that kind of capability into a complex humanoid, 125 kilograms, about 160 centimeters tall, with very advanced electronics and actuation systems.
From the very beginning, we wanted an upper body that was built for biped locomotion. This marks the 20th year of our Robonaut program. Our view of the Robonaut system is it's really only half humanoid. Over the years, we've put them on 2 wheels, we've put them on a stanchion, just fixed. We've had them on 4 wheels, we call the Centaur configuration. Wheels are wonderful. I'm a big fan of wheels. They're one of the best inventions ever. But once you try and climb inside a spacecraft, wheels are pretty awkward. You're inside a capsule. Space is at a premium. Everything will be nested in, curving walls and shape. What you would rather is to have feet that can work on steps and climb ladders and work around pretty complicated geometry. Those spacecraft are going to be built to count on humans' athleticism. People will handle it just beautifully. If you ask a person to climb through a tunnel and turn around and then go back down a stair or a ladder, we're amazingly athletic and we're able to do that. Instead of making the world adapt to the robots, it's already built for people. And essentially, we're accepting humans as the de facto standard. The 2 legs that we've built for Robonaut, they're really optimized for zero gravity. This is not human, but we now have the technology to build a machine that can fit into a space built for people.
But we're not there yet. We're very far away from being able to achieve the capabilities of a human can do, the capabilities that a child of 2 or 3 can achieve. It's a long distance away from where robots are. Previous generations, for example, of the Atlas robot operated with a power cable that was providing power from an external source off board, while the Asimo previous generations of it could only pick maybe a half a kilogram up. Each new generation and each new prototype of these robots is bringing a new capability, and hopefully we move towards systems that can work in the real world or space exploration like NASA are interested in. It requires painstaking development, typically semi-manual implementation of algorithms that have to be refined and tuned so that we can finally get at an algorithm that can precisely detect and understand.
It is a technological challenge to build a platform like Valkyrie, but there's a whole another challenge trying to get it to do anything you want after you've built that kind of core capability. This is not just a one-to-one relationship. We are collaborating with MIT as well as IHMC, university and a research firm in Florida. So it's a very close-knit collaboration between these 3 institutions towards the control of these robots.
The project sort of spans several work sites in America. There's a lot of moving parts. But the philosophy of the group that I come from is basically always been, let's build the robot so that it can work and we can do the work on it just in our lab without a whole lot of special equipment. And that's been well for us. I mean, it's having, to run it in the lab here, we brought a power supply and said, we need you to have some kind of gantry so that we can hang the robot up. And that's the entirety of the equipment that we've asked for.
It's a very expensive robot. It falls all of the time. It's got engineered padding to support itself, but a motor or a cable that's damaged essentially means no signal, and as a result, it simply won't work. So we use the support mechanisms as a precaution. When you look at the difficulties it is to make a very complicated system such as a robot to be able to stand, to balance on 2 feet, it requires every single component of it to be working, to be tuned, to be precisely refined.
Because of its form factor, people tend to empathize with it. We think of it like an entity, a he or a she, but it is actually a machine. Essentially, it is built out of motors and sensors and some programs and AI underlying it, which is making it move. The process of transferring human volition into a motion on a humanoid robotic platform is much more complicated than we think. You get a high-level goal, like the robot has to walk up to a table, pick up something and manipulate it. That has to be broken down into multiple steps. So first, it involves planning a path that is collision-free, that maintains stability and achieves the goal of reaching within the limits of the robot's capabilities. The second element is using the sensors that are in the robot to actually estimate the state of the world and then realize the actual affordances in the grasping and manipulation. And finally, you also have to worry about the real-time control. Valkyrie receives commands at about 1000 Hertz, which means every second it receives about 1000 control commands. So getting the control, the planning and the sensing and state estimation right to achieve that volition is a very complex process.
The way that robots get stronger is by braking. It's kind of like exercise. If you only exercise one way, those muscles are going to get really strong, and so we've exercised the robot the way that we exercise it for a long time, and those muscles, those parts of the robot are very strong. But it's nice to have somebody that's got a different focus of their research to come in and exercise the robot a different way.
Our spacecraft, they're designed for very athletic people called astronauts. And as a result, they're pretty hard to get in and out of. Being able to be athletic, where you're coordinating your upper body and your lower body, where you're balancing using your hands and taking the weight with your feet in a very coordinated and smooth way. That's something that robots don't really do today, but I'm seeing those algorithms being developed here at Edinburgh, and I'm excited to see how they get tested on this robot and get put into the designs maybe of our next generation.
Society has a habit of envisaging a physical system having the capability that they see on first principle, on first approach. But what's hidden is the technology that's going on, the algorithms to do 3D mapping and the algorithms to footstep planning. It requires a lot of integration to put pieces working together. The miracle of humanoid robots, or the miracle of robots, is when they actually operate and behave by themselves. It's a very complicated domain. But when things work, it can be quite beautiful because of the complexity that goes on behind it.